So a few points that I wanted to quickly get across. One is we talk about the origin of life, and I think it's important to try to figure out like the origin of what are we talking about. And often we think of the origin of being alive as the thing that we want to explain. But if we can explain the origin of coffee cups, we will explain the origin of life. If we find the equivalent of a coffee cup on Mars, we will have found life on Mars. So the origin of life is not the equivalent of the origin of alive. And I think it's important for the field to make this distinction, that we want to understand how life evolved. Whether or not being alive also evolves at the same time is a separate question. And I wrote a piece with Sarah Walker about this in Aeon, so you can Google. Right? Okay. Second point is about individuals and replication. So I'm an evolutionary theorist, and evolutionary theory often implies that we are talking about a population of individuals that replicate, and selection acts on these individuals. But let's look at ourselves. So I will never replicate. There will never be anyone like me, luckily. And I got half of my chromosome, half of my genome from my mother, half from my father, my mitochondria from my mother, my Y chromosome from my father, ideas from this amazing symposium, the microbiome partially probably from my mother and partially from the lunch I ate yesterday. So we are I'm a collection of lineages that came together in me for some time, some of them during my life, some of them will go in and out. Now they're going out. And so I think that we should think of evolution as acting on these, we should think of evolution as acting on these lineages of information that go through individuals. Individuals here are these bundles of these lineages that otherwise just flow through us and continue. I think that should be the major view of how evolution works, and not thinking of evolution as individuals that replicate and selection on individuals. And once we do that, then we can, I think much more fruitfully about the origin of life. Oops, sorry. And of course, Woe said this about the pre-Luca world, that pre-Luca, there were like many different lineages, and there's not a single Luca. Then it's much easier to then talk about cultural evolution, the free market, and as I said, real organisms where lineages come together. So I think this is the major way we should think of the evolutionary process, and not individual. Of course, individuals are important. Each lineage that I'm talking about here is, in a way, on it acts something like the evolutionary process as evolutionary theory currently talks about. But if we want to understand the origin of life, it's very likely that what happened there is not a single self-replicating molecule, but instead a collection of lineages that acted together. Finally, and this is not a soapbox anymore, I wanted to talk about how information is gained in evolution. So information is gained in evolution through selection. Selection weeds out some of the lineages, and some of the other lineages stay behind. And it's easy to show that there is this limit on how fast information can be acquired. If W is the proportion of lineages that survive, then the amount of information that can be gained is minus log W. And here we see an example. So initially, maybe the genome could have an A, C, G, or T, and we put it in 4 possible environments. Environment 1 selects for A, 2 for C, and so on. In each environment, a quarter of the lineages survive. So W is a quarter, and the information gained is exactly 2 bits of information. Minus log a quarter is 2 bits. And you see that we started with 4 possibilities. We ended with 2, which is 2 bits of information. So this is the limit of how fast information can enter the genome. with sexual production, and right, I talked before about how it's important that I got half my genome from my mother, half from my father. It turns out that with sexual production, this limit does not exist. So I have 2 parents 1 generation back, 4 parents 2 generations back, 8 parents, 8 ancestors 3 generations back, and so on. This way I can gain much more information about selection than a single asexual lineage could. And so the limit that I talked about before, minus log W, does not exist for sexual production. Actually, with sexual production, there's no limit on the amount of information that can enter the genome per generation, limited by selection. And I could talk about this later, but it's just a comment. Okay. So the origin of life has interested people forever, right? And religion gave explanations for it, and so, and why is it so important to explain the origin of life? What's the point? I think one of the points is that when we look at things that are part of life, things that are alive, they have a lot of function in them, a lot of purpose. We see an ant walking and we kind of almost step on it and it runs away, or plants grow towards the light, or we can, when we look at this moss, we can ask, what is this part for? What is this part for? And so on. So function is very important for life. Whereas when we talk about the non-living world, there's no function. We can't talk about function. And so, and purpose. So I think part of the reason that we want to understand the origin of life is understanding the origin of purpose. How did purpose in these living things emerge out of non-purpose in the non-living world? And this is related to questions that we asked yesterday and the day before about the functionality of metabolism, right? That in metabolism, it's important that metabolism is acting on a certain purpose. How did that purpose emerge out of a chemostat or like some mixing of reactions where there is no purpose? So I think this is the thing that one of the things that we try to explain when we explain the origin of life. Okay, now the main part of my talk. And this is very similar to, oh, people don't sit in the same place, but they always do. There. This is very similar to what Lauren said. So when we talk about evolutionary theory, we know that we talk about replication, variation, and selection that act together in a certain way. And because of this, it seems that replication is really important. So we try to explain, when we explain the origin of life, we'd like to understand how replication emerged. How were there the first self-replicating molecules? But I think what I want to do is I want to look, instead of looking at replication, I want to look just at selection. So selection without replication. And I think that selection without replication, so selection without replication, we have pre-existing variation, and then some of the individuals or entities are selected out and some remain. This is a selective process. Some people call it a sorting process, but I don't think it matters much. Examples for how selection can act outside of biology are everywhere. So here, for example, is nuclear decay. So there is a nuclear disaster, and radioactive atoms are released into the atmosphere. If we come after one minute, there's a lot of radioactive atoms. If we come 5 years later, all the really radioactive atoms already decayed, and what is left is slightly less radioactive atoms. And if we come after 10,000 years, there will be even less radioactive atoms. So there is this selection process for being less and less radioactive. This is a famous, favorite example of mine, which I won't go into, but even, rocks on the hill, when they can roll down the hill, and there can be a selection process for staying on the hill. And what I want to do now is I want to take this a very, very simple system, a system of an ideal gas, and see how selection can act here in order to explain to us a bit about the thermodynamics of selection. Of course, I'm talking here about thermodynamics to a population of partly chemists who know thermodynamics way better than me, which isn't hard. So probably most of what I say you already know. I want to talk about the one-dimensional ideal gas. And when I will talk about the one-dimensional ideal gas, I will talk about the phase space of a single molecule. So this dimension is the x-coordinate of the molecule. So it's one-dimensional. It only has one x-coordinate. And then this dimension is the momentum. And so this space is called the phase space of the molecule. And here you see a single molecule as it moves through this phase space. So its location changes over time. And that depends on its momentum or its speed. So the speed determines how fast it moves here. And if we had a second molecule, then now this molecule has a higher speed and therefore it moves faster through the x-coordinate. Now we can talk about an ensemble of molecules. So these are lots of molecules. This one is at coordinate 0, this is 0.1, and so on. And they have different speeds. And I will talk about what this ensemble does as it moves through time. And, whoops. Okay. Now, an important part that I will gloss over because I threw out most of my slides when I prepared this talk. I'm talking here about selection outside of biology, and therefore the notion of being alive or replicating doesn't exist, and I have to somehow define what do I mean here by selection. So the way I talk about selection for in general in systems is that I say take the phase space of a single entity, and then in that phase space I outline a region where I say here is where the entity is alive or in, I call it in, and then the rest of the region is where it's in out. And I'm looking at the selective process of staying within region in, as opposed to moving out of the region. So for these molecules that are in the one-dimensional bottle, the selective process that I look at is staying inside the bottle. So the bottle is between a coordinate point minus 0.5 and 0. This is the bottle. And now I let the gas escape on the right end. And oh, by the way, I'm only looking at positive speeds. There's also the negative speeds here, which if by talking only about positive, it makes the discussion a bit easier. So, but it doesn't change the results that I'm showing. I'm looking at the molecules escaping out of the bottle. And now let's see what happens with molecules as time proceeds forward. And you see that they slowly move out of the bottle. Molecules that have a faster speed move out of the bottle faster. Molecules that have a slower speed, those that have 0 speed, stay in the bottle. And the slower they are, the more likely they are to stay in the bottle. And so, of course, this is a process that we know. If we have a bottle full of gas, we release the gas cools down. And what I'm claiming here is that we can interpret this process of the gas escaping in terms of selection. There's selection for slower molecules staying behind in the bottle. And you can also see that, so the molecules that are in the bottle are now colder. Their entropy supposedly was reduced. The entropy was decreased inside the bottle. And this is exactly the process of selection, right? So selection selects for certain properties of the entities, and that process is a reduction in entropy in those particular degrees of freedom. So we see here that something very similar to what happens in an evolutionary system happened here. 10 minutes. Good. Okay, so now I'm claiming that we can talk about this system as a system where we can look at selection. This also means that we can apply evolutionary theory to this system. We can apply theorems like the price equation, Fisher's fundamental theorem, to look at what happens to gas as it escapes the bottle. Yeah. Why does it move to? Okay. Now what happens here is that we started with gas inside the bottle, and then we let the gas escape. So initially, there was a free energy that was there because the gas was in the bottle. Outside there was a vacuum. With this free energy, we could have run an engine or made ice cream or whatever, right? That was free energy that was available to us. And as we release the gas, this free energy is now released. And the process of selection used this free energy in order to generate information about how to stay in the bottle. And this information for how to stay in the bottle was, it's good to be slow. And we can look at the thermodynamics of this. And for this, it's good to use something that's called the Kolbeck-Leibler divergence. And Kolbeck-Leibler divergence, in general, it's used to ask questions like, how much would you lose if you think Q instead of P? P is the truth and Q is what you think. How much would there be a loss? How much information would you lose if you listen to the wrong weather report? Or you tried to compress a file that you thought was music, but it's actually an image. Okay, and Kolbeck-Leibler is tightly linked to free energy. And the way that we can link Kolbeck-Leibler to free energy is that we say, what's the distribution in the system currently, and what's the distribution in the system at equilibrium? The distance between these two tells us how much free energy is in the system. And this is tightly linked to this thing called the Landauer's principle, which says how much information, how much free energy do we need to erase a single bit of information in memory. So this would be kT log 2, and this is very similar, kT of the Kolbeck-Leibler distance between the equilibrium and what we currently have. So what happened here is, right, I said that we started with gas inside the bottle, and that had free energy. The free energy, we could measure it by the Kolbeck-Leibler divergence, right, the distance between this and this equilibrium distribution. Now the gas is escaping. Here I'm pulling maybe a fast one because this is not exactly a state that we can use the Kolbeck-Leibler, but we get to this state. Now half the gas escaped and half stayed behind. And what we see is what happened is that initially the information was about being inside or outside the bottle. Now after the gas escape, we have information about being fast or slow. And we lost this information about whether you're inside or outside the bottle. So the initial free energy that was about inside and outside was converted into functional information. Functional information here is about being fast or slow, and there's still a leftover of information of inside or outside. So what we see is that we can interpret this selection as a process that converts the initial free energy into functional information, which is also functional free energy. I hope I probably lost everybody. Okay, so what I'm claiming is that the selection process can act in many systems, and in the systems where it acts, it generates functional information. So this means that functional information is prevalent all over physics in every system, and the difference between biology and non-biology, between post-life and pre-life, is not do you have or not have functional information, instead how much do you have it. And so I think that this, I would like to not propagate, what do you say, raise the idea of selection first. Selection is, I think, one of the first processes that happened. And after that, we can talk about how purpose and function were generated during the origin of life by selection. Okay, I really don't have time. I should finish, right? Yeah. Okay. So now I was talking about single molecules, but of course organisms aren't single molecules. So what happens when we talk about slightly bigger organisms? Let's look at an entity that's built out of two molecules, two atoms. And so we take exactly the same system. The atoms aren't bound, but we just simply look at what I call an organism, which is simply two molecules that are near each other in phase space. And now, as time goes on, these two molecules will either both escape or both stay behind. And since we just paired molecules that were there before, we just paired them into these pairs that we call an organism. Of course, nothing in the dynamics changed. So we have now half the molecules escaped and half stayed behind, maybe. And that means that if before we had maybe, say, 1,000 molecules in the bottle and we let 500 leave and 500 stayed behind, now we just had 500 pairs, 250 left and 250 stayed behind. So the same process happened, but on pairs, right? And to form a pair of molecules in a certain place, of course, costs more. It costs double what it costs to do one molecule. So it seems like we had to invest more energy in creating this, right? Of course, it wasn't really more because we had less entities that we generated, and we have now only 250 pairs that know that they should stay behind, each of which is built of two molecules. So it seems as if by pairing we lost something, right? Somehow before we had 500 times the information, now we only have it 250 times. The solution is, what you see here is that actually, just as before each of the atoms that is inside now has a slow speed, each of the atoms that's outside has a fast speed. Now, each of the atoms of the pair, has the same. Okay, I'll just. Okay, I think. Yeah, I'll just jump over it. Okay. So here I was talking about just selection, but of course replication is important. And I would like to understand what is replication for? Why is it important? So if we have a system like this with no selection, no new individuals, eventually we run out of individuals. As most individuals die, we are left with just one. If we just put new individuals in, we put more gas into the bottle, we lose on the information that we had. So this slow gas, the low temperature gas disappeared, and now we diluted the signal that we got from selection. If we have replication, we can continue selection, and then we have, eventually we'll end up with, in this particular case, a much, much colder gas, if we could replicate the state of a molecule. So replication allows us to do more and more selection, and okay. And it also allows us to get the information for very cheap. So here initially, we needed to get the information by doing selection, but if we copy the information, now we get the information simply by a copying process. So it's much cheaper to generate the information again. Okay, so the summary. We should look at the origin of life and not of being alive. I think the origin of being alive is a separate question. We should think of how the emergence of symbiosis and what symbiosis did at the origin of life, and not try to focus on how did individuals that replicate emerge. And finally, selection converts free energy to functional information everywhere. So in a sense, we could say that selection came first. That's it. Thank you.